Welcome, students. Today, we're doing something really exciting. We're stepping away from the usual rote memorization, and we're diving headfirst into the beautiful, highly predictable patterns that actually govern our world. I mean, think about it. If you've ever looked at the spirals on a pineapple, the petals on a sunflower, or even just watched how a savings account grows over time, you are looking at mathematical patterns in action. In this explainer, we're going to build complete conceptual mastery of Chapter 5 from your math curriculum. We aren't just going to memorize formulas today. Oh no, we're going to literally crack the code of exactly how and why those formulas work. So, you ready? Let's dive right in. Okay, we're kicking things off by looking at 3 totally different real-world scenarios straight out of your textbook. Now, at first glance, these have absolutely nothing to do with each other. We've got a young professional starting a brand new job, a mother saving money for her daughter's birthdays, and a pair of breeding rabbits. It sounds like the setup to a weird joke, right? But underneath the surface, they actually all share a hidden mathematical secret. They are all sequences of numbers. But the real question is, how do those numbers grow? Let's break them down. Imagine we're putting a magnifying glass right over the numbers in these 3 scenarios. First up, Reena. She just got a job starting at 8,000 rupees a month, with a guaranteed 500 rupee raise every single year. So her salary tracks like this: 8,000, then 8,500, then 9,000. Next, we have Shakila. She puts 100 rupees in her daughter's money box on her first birthday and increases that gift by 50 rupees every year. So that sequence is 100, 150, 200. Finally, the rabbits. They produce a new pair every month after their first month, so that population goes 1, 1, 2, 3, 5, 8. Notice something? Look at how Reena and Shakila's amounts grow by a fixed, predictable number every single time. Reena always adds 500. Shakila always adds 50. But the rabbit population? That jump changes every single month. It grows totally differently. Now let's look at another pattern that breaks our special fixed jump rule. Imagine you're building squares out of blocks. The first one has exactly 1 unit square. The second one has 4. The third has 9. Well, to get from 1 to 4, you have to add 3. That to get from 4 to 9, you have to add 5. Because that jump changes, first it's a jump of 3, then suddenly it's a jump of 5, this is emphatically not what we call an arithmetic progression. For a pattern to be in our special mathematical club, that jump absolutely cannot change. So that brings us to the absolutely crucial point of today. Here is our grand definition. An arithmetic progression, or AP for short, is simply a list of numbers where the gap between any 2 consecutive numbers is always exactly the same. Actually, scratch that. It's not just a list, it's a very specific chain. You take a starting number, you add a fixed amount to get the next number, you add that exact same amount to get the next one, and so on. That fixed amount, that is the heartbeat of an AP. To master APs, you really don't need to memorize a massive dictionary of terms. You honestly just need to meet 2 new best friends. The first is the letter A. A simply stands for the first term. It's your starting line. The second is D, which stands for the common difference. This is that fixed jump you take each and every time. If you know A and you know D, well, you basically have the complete DNA of the entire sequence. You can build it outwards forever. And speaking of forever, we actually categorize APs into 2 simple types. Just like in real life, some patterns eventually stop. If you line up students for a morning assembly by height, maybe the line starts at 147 centimeters and ends at 157 centimeters. It has a definitive last term. We call that a finite AP. But other patterns, like counting basic integers, 1, 2, 3, 4, they never stop. They spiral out into infinity with no last term in sight. Those, naturally, are infinite APs. Let's visualize this together. Imagine an arithmetic progression is exactly like climbing a ladder. The very first rung at the bottom, where you place your foot to start your climb, that is our A, the first term. Now, the physical distance between that rung and the very next one, and honestly, every single rung after that, is our common difference, D. Because a well-built ladder is perfectly uniform, that D is always going to be the same. Let's see how this builds step by step mathematically. You're standing on the first rung. Where are you? Well, you're just at A. To step up to the second rung, you take your starting position, A, and you add 1 jump, D, so your second term is A plus D. To get to the third rung, you add another D. Now you're at A plus 2D. To reach the fourth rung, you guessed it, you are at A plus 3D. Now look really closely at those numbers. To get to the fourth rung, how many times did we actually add that gap D to our starting point? Exactly, 3 times. We added 3 Ds to get to the fourth rung. We added 2 D's to get to the third rung. The pattern here is undeniable. You don't add the difference to the first term to get the first term, you're already standing on it. Which is exactly why the multiplier for our jump D is always 1 less than the term number. If we call the term number we are looking for n, then we are always multiplying our jump D by n minus 1. Boom! Look at what you just did. You didn't just memorize a formula today, you logically derived it all by yourself. If you want to find any term in an arithmetic progression, let's call it the nth term or a sub n, you just take your starting point a and you add your jumps. And how many jumps is that? It's n minus 1 jumps of size d. This right here is the universal blueprint. This equation is like a time machine that allows you to jump to the 100th, 1000th, or even millionth step of a pattern without having to painstakingly add everything up manually in between. Okay, let's take this new superpower out for a spin on a real-world scenario from earlier. Remember Reena? She started at 8,000 rupees and got a 500 rupee raise every year. Let's find out exactly what Reena's salary will be in her 5th year on the job. Let's extract our variables. Our starting point A is 8,000. Our common difference D is 500. The term number we want to find n is 5. So we are officially looking for a sub 5. Let's plug all of this into our blueprint. We substitute our known values directly into the formula. A sub 5 equals 8,000 plus, in parentheses, 5 minus 1 times 500. Let's simplify those parentheses first. 5 minus 1 is 4. And hey, this makes perfect sense, right? By her 5th year, Reena has received exactly 4 raises. So we multiply her 4 raises by the 500 rupee jump, which gives us 2,000. Finally, we just add that 2,000 to her starting salary of 8,000. And there it is, 10,000 rupees. Reena is going to be making 10,000 rupees a month in her 5th year. Notice how we didn't have to write out year 1, then year 2, year 3, year 4, and year 5. We just vaulted straight to the answer. This proves that algebra isn't just a bunch of random numbers on a page, it's an incredibly powerful tool to predict the future with absolute certainty. Now, before we wrap up this foundational explainer, I want us to ask a really critical question about the nature of our jump variable, D. In Reena's case, she was getting a raise, so her D was a positive 500. Her numbers were climbing up. But does D always have to be a positive number? Does the ladder always have to go up? Absolutely not. From your textbook examples, we see that D can actually take on a few different personalities. Yes, for sure, it can be positive, like Shaquila's money box adding 50, so the numbers increase. But D can also be negative. Look at the sequence, 8, 5, 2, negative 1. To get from 8 to 5, you have to subtract 3. So here, the common difference D is negative 3. The pattern is literally walking down the stairs. And amazingly, D can even be 0. Consider the sequence 3, 3, 3, 3. The jump is 0. It's an entirely flat road, but guess what? It still fits our strict rule perfectly, making it a valid arithmetic progression. So look at what you've accomplished today. You've mastered how to identify an arithmetic progression. You completely understand its anatomy, the starting line A and the jump D. And you've successfully derived the formula to pinpoint any specific step in that pattern, no matter how ridiculously far into the future it is. But I want to leave you with a bit of a brain teaser. What happens when you need to calculate the sum of the entire sequence? What if Shakila wanted to know the total cumulative amount of money in the box after 10 years and not just the small amount she put in on that 10th birthday? How do we mathematically collapse an entire sprawling sequence into one single sum without spending 3 hours punching numbers into a calculator? Keep that in mind because that is the next incredible mathematical code we're going to crack. Keep looking for those patterns around you, and I'll see you in the next explainer.
Welcome back, everyone. I am so incredibly excited for today's explainer. We are going to unlock what I genuinely think is one of the coolest, most satisfying magic tricks in all of math. We've already spent some time building arithmetic progressions, right? Term by term. But today, we're taking it to the next level. We are going to master how to find the total sum of an AP. And hey, we're not just memorizing a random formula here. No way. We're going to dig into the brilliant, elegant logic behind it, so you understand it literally from the ground up. Let's get into it.
Okay, picture this. You're sitting at your desk, and I ask you to add up the first 100 positive integers manually. So 1 plus 2 plus 3 plus 4, all the way up to 100. Honestly, how long is that going to take you? It'd be completely agonizing, right? You'd be carrying over numbers, probably losing your place. It's just brutally tedious. It's totally natural to look at a mess like that and think, man, there has got to be a shortcut. Well, let me validate that feeling for you right now. There absolutely is.
And the answer is 50-50. That's it. No calculators, no giant messy pages of scratch paper, just boom, 50-50. So, how on earth can we hit that massive sum in just a matter of seconds? What is the hidden architecture behind these numbers that lets us completely bypass all that manual adding? Let's basically break out the whiteboard here and visualize exactly what's happening.
All right, I want you to imagine writing out a general arithmetic progression from left to right. Let's just call the total sum S. The first term is A, the next one is A plus D, and so on, all the way to the last term, which we already know is A plus n minus 1 times D. We'll call that equation 1. Now, right underneath it, I want you to write the exact same sequence, but completely in reverse. So equation 2 also equals S, but it starts with that big last term, A plus n minus 1 times D, and counts all the way backward down to A.
Now here is the massive aha moment. Look at what happens when we add these two equations vertically, straight down the columns. Take the very first column. We add A to A plus n minus 1 times D, and we get 2A plus n minus 1 times D. Now look at the very last column. We add A plus n minus 1 times D to A, and what do we get? The exact same thing, 2A plus n minus 1 times D. Every single vertical pair in this entire setup adds up to the exact same uniform value. And this identical pair, it repeats exactly n times.
Let's look at how this builds out algebraically. Because we essentially added the sum to itself, we now have 2s sitting on the left side of our equation. And over on the right side, we have our uniform block, 2a plus n minus 1 times d multiplied by n, simply because there are n terms in our sequence. But hold on, we don't want twice the sum, right? We just want the actual sum s. So what's the move? We just divide the entire right side by 2. Think of it like a perfectly balanced scale. We just cut both sides in half to find our true target.
And there it is, the absolute game changer. We have officially derived the universal formula for the sum of the first n terms of an AP. S equals n divided by 2 multiplied by the entire quantity of 2a plus n minus 1 times d. Let's just quickly break down its atomic components so it's totally locked in your brain. S is your total sum, n is the number of terms, a is your starting term, and d is that common difference. With just these basic ingredients, you can find the sum of literally any arithmetic progression you come across.
But hey, math is all about efficiency, right? And sometimes we can actually shortcut the shortcut. Look really closely at that 2a inside the brackets. What if we break that 2a apart into just a plus a? Now look at the chunk of the formula sitting right next to it, a plus n minus 1 times d. Does that ring a bell? It definitely should. That's our old friend, the formula for the nth term of an AP, just hiding in plain sight. If the sequence is finite, that piece represents our very last term. So we can just replace that whole messy chunk with the letter L, or sometimes you'll see it as a sub n, which just represents the last term.
And that brings us to this incredibly sleek, lightning-fast alternative formula. S equals n divided by 2 multiplied by the quantity a plus L. This is such a beautiful variation to keep in your back pocket. Why? Well, because if a problem happens to hand you the very first term and the very last term right out of the gate, you don't even have to worry about figuring out the common difference. You literally just plug them right into this alternate formula, multiply by half the number of terms, and boom, you are immediately at the finish line.
Now, watch how perfectly this connects straight back to that opening trick with the numbers 1 to 100. If we use our new alternate formula, our a is 1, and our last term, L, is n, which is 100. So the formula becomes S equals n times n plus 1 all divided by 2. By the way, this is actually a really famous special case specifically for the sum of the first n positive integers. So for our 1 to 100 problem, we simply take 100, multiply it by 101, and divide by 2. Let's see, 100 times 101 is 10,100. Divide that in half, and there it is, 50-50. That is the raw, undeniable power of algebraic patterns.
Okay, now I really don't want you thinking this only applies to abstract numbers just floating around in space. Let's ground this in the real world. Consider this scenario involving a mother named Shakila. On her daughter's first birthday, she drops 100 rupees into a piggy bank. Now on every birthday after that, she increases the amount she puts in by exactly 50 rupees. So the sequence goes 100, then 150, then 200, and so on. We want to figure out exactly how much total money is sitting in that piggy bank by the daughter's 21st birthday. We can map this real-life timeline straight onto our mathematical framework. Our starting amount, that first term A, is 100. The fixed amount added every single year, our common difference, D, is 50.
And the total timeline, our n, is 21 years. Now, we don't actually know the last term here, so we're going to use our main formula. Let's plug it all in carefully, step by step. S equals 21 over 2 multiplied by the bracketed quantity, 2 times 100 plus 21 minus 1 times 50.
If we just follow the standard order of operations, inside those brackets we end up with 200 plus 1,000, which is 1,200. Multiply that by 21 over 2, and we reveal the final total sum, 12,600 rupees. Just think about how genuinely powerful this is. Instead of sitting there manually writing out 21 different bank deposits and tallying them all up one by one, we structurally defined the pattern, fed it into our formula, and extracted the exact total instantly. It's like a superpower.
All right, before we jump into some rapid-fire examples, there is a really crucial, kind of hidden relationship mentioned in the text that you absolutely need to understand conceptually. The nth term of an AP is always equal to the difference between the sum of the first n terms and the sum of the first n-1 terms. Let me translate that into plain English. If you know the sum of the first 10 terms of a sequence, and you subtract the sum of the first 9 terms, what's left over? Literally just the 10th term itself. It makes perfect intuitive sense when you visualize it that way.
Okay, we're going to accelerate the pacing a bit now and tackle a rhythmic textbook problem. Example 11. We need to find the sum of the first 22 terms of this specific AP. 8, 3, -2, and so on. First step, as always, map out your variables. Our starting term A is 8. Now, you got to be careful with D here. 3 minus 8 is -5. So our common difference is negative, and n, the number of terms we're summing up, is 22.
Let's plug this straight into our master formula. We get 22 over 2 times the quantity, 2 times 8, plus 21 times -5. That simplifies really nicely to 11 times the quantity, 16 minus 105, which gives us 11 times -89. And the final result? Confidently -979. And this is so cool because it proves that our formula works absolutely flawlessly, even when our sequence is diving deep down into negative numbers. The underlying structure holds up perfectly.
Taking a quick step back, I really want to prove to you that arithmetic progressions exist in physical space, not just on your exam papers. Take a look at these examples of a ladder and some concrete terrace steps. These aren't just random objects, they are literal physical manifestations of APs. Whether it's the uniform decrease in the length of ladder rungs or the uniform addition of concrete volume for each sequential step, nature and engineering constantly rely on the rules of arithmetic progressions to build stable structures.
Think about that ladder, for instance. Let's say we're told that the bottom rung is 45 centimeters, and they decrease uniformly into the top rung is 25 centimeters. Uniform decrease? That is the secret code phrase for an arithmetic progression. Now, if we needed to calculate the total length of wood required to build all those rungs, we have the first term, 45, and the very last term, 25. So which formula do we use? Our sleek alternate formula. S equals n over 2 times a plus L. It perfectly models this real-world geometry without skipping a beat.
Wow. Okay, we have covered a tremendous amount of ground in this explainer today, pulling back the curtain on how these sequences behave right down to the atomic level. Now it is time to synthesize everything. Let's bring all the foundational concepts of Chapter 5 together into one big picture summary so you can walk away today with complete conceptual mastery.
First up, the core rule. An AP is really just a list of numbers where you get the very next term by adding a fixed number d to the previous term. That is its fundamental DNA. Second, the general form is always a plus d, a plus 2d, and so on forever. And third, if you ever need to sort of snipe a specific term out of a massive sequence, your best tool is the nth term formula. A sub n equals a plus n minus 1 times d.
And finally, our major achievements from today's explainer. When you need to sum up an entire sequence, you now have two incredibly powerful tools. The primary sum formula, S equals n over 2 times the quantity 2a plus n minus 1 times d. And if you are lucky enough to already know the very last term, you deploy the incredibly fast alternate formula, S equals n over 2 times a plus L. Remember, these aren't just random letters. They are the structured mathematical translation of that incredibly clever trick of adding sequences forwards and backwards.
So as we officially wrap up this explainer, I want to leave you with a bit of a challenge. Look around your room right now. Seriously, look out your window. Is it the rungs on a chair? The stacks of bricks on a wall? Maybe the way savings grow in a bank account? Where can you spot a hidden arithmetic progression hiding in plain sight? Because I promise you, Once you understand the math, you start seeing the matrix everywhere. Keep exploring, keep questioning, and I will catch you in the next explainer.
Welcome to this Masterclass Explainer. Look, I know you're gearing up for the highly competitive Karnataka SSLC board exams, and I know you've already got the mathematical basics down. You know what an arithmetic progression is. But today, we're not just doing textbook math. As a veteran SSLC evaluator, I'm going to show you exactly how to crack Chapter 5 and squeeze out every single mark. We'll be looking at the official model answers and evaluation schemes to see exactly where students bleed marks, and more importantly, what we examiners are desperately looking for in your paper. Okay, let's jump right in with a golden rule straight from the grading room. Picture this. I've got a stack of hundreds of papers to grade. I don't just glance at the bottom of your page for the final number. No way. We are strictly guided by a marking scheme. We are actively hunting for specific value points to award you marks. If you don't write down the exact step that matches a value point, I literally cannot give you the mark, even if your final answer is 100% perfect. Understanding this one fact changes absolutely everything about how you write your exam. So here's our evaluator's playbook for today. First, securing that 1-mark MCQ speed. Second, the half-mark formula rule. And finally, avoiding those tricky 2-variable elimination traps that cost students thousands of marks every single year. Let's get into it. All right, let's kick things off with the 1-mark speed run. This specific type of question is an absolute favorite for the examiners in the multiple choice section. Straight from the official key answers, it asks, if the nth term of an arithmetic progression is an equals 24 minus 3n, what is its second term? Now, a lot of students instantly panic here, or they start doing massive long-form calculations. But remember, this is only worth 1 mark. Your strategy needs to be lightning fast. This brilliantly shows the difference between someone just memorizing a textbook and a true exam cracker. The slow method? That's calculating the first term, then trying to figure out the common difference, and building the whole sequence. Please, don't do that. Do not waste your time finding the entire sequence. To grab that mark instantly, you just use rapid substitution. You want the second term? Just substitute n as 2 immediately. It becomes 24 minus 3 times 2. That's 24 minus 6, which gives you 18. Boom, done. You've secured the point in 10 seconds and saved your brain power for the long answer section. Let's move on to another massive MCQ trap. Take a look at the sequence, 8, 5, 2, -1. The question simply asks for the common difference, or D. Looks ridiculously easy, right? But as an evaluator, let me tell you, whenever I'm grading this specific question, I literally get my red pen ready because I know exactly what mistake is about to happen. Here's the trap. The answer is -3. Why? Because the official formula is strictly A2 minus A1, second term minus the first term. But students constantly look at the numbers 8 and 5 and just logically subtract the smaller number from the larger one, writing down a +3. You've got to remember, when a sequence is decreasing, subtracting a larger number from a smaller one gives a -D. Dropping that negative sign is a careless mistake that routinely ruins perfect scores. Now, moving on, the strategy shifts for the 2- and 3-mark written questions. I like to call this the half-mark hunt, and it entirely revolves around what we examiners call the formula-first policy. When you hit a descriptive question, you need a psychological shift. Stop trying to solve the whole problem in your head and immediately start writing down the fundamental rules. Seriously, take a look at this official scoring blueprint. As an examiner, I want to give you marks, I really do, but you have to show me the steps on paper. Simply writing out the base formula, like an equals a plus n minus 1 times d, guarantees you a half mark instantly. Even if your arithmetic goes completely off the rails later in the problem, you've locked in that half mark just for showing us you know the right tool to use. The next half mark, that's literally just for plugging the numbers from the question into that formula. Bottom line, don't skip steps and always write the formula first. And the crucial point is right here during the substitution and solving phases. Let's look at a classic 3-mark evaluation from the board. You've set up your 2 equations perfectly. A plus d equals 8 and a plus 3d equals 0. You go to subtract equation 2 from equation 1. The a cancels out perfectly. But then students write 2d equals +8. Trap! It's 0 minus 8. It should be 2d equals -8, which means d equals -4. Dropping that negative sign so you write d equals 4 instead of -4, that will literally cost you 2 full marks because it completely ruins every single calculation that follows. Always double check your signs. To give your brain a quick, high-yield memory aid before we tackle the big word problems, I want you to remember this giant number, 50/50. This is the sum of the first 100 positive integers. It's instantly calculated using our SN formula. n divided by 2 times the sum of the first and last terms. So 100 over 2 times 1 plus 100, that's 50 times 101, which gives you exactly 50/50. Memorize this specific example. Examiners absolutely love using it as a baseline to see if you conceptually understand the sum formulas. All right, now let's tackle the 4-mark word problem boss battle. We're looking at an actual board evaluation blueprint here for a problem about a shop worker's 6-day earnings from Monday to Saturday. His total earnings from Monday to Wednesday are 525 rupees, and on Friday he gets 100 more than Monday. Sounds like a lot, right? Well, let's break down exactly how you can form all 4 marks out of this complex paragraph. The single most important step in these word problems is literally translating the English words into AP terms. Just writing, let the income be A plus D, A plus 2D, A plus 3D unlocks your first half mark before you even do any heavy algebra. From there, the problem states the sum from Monday to Wednesday is 525. So you write out A plus D plus A plus 2D equals 525. Simplifying that to 3A plus 3D equals 525 earns you a whole 1 mark. Think about that. You're already at 1.5 marks just for translating a word problem into a math equation. Next, you translate the second condition. Friday is 100 more than Monday. That means A plus 4D equals A plus 100. The A's cancel out beautifully, leaving 4D equals 100, so D equals 25. Bam, another half mark. Substitute that back into your first simplified equation, and you find that A equals 150. That's another half mark secured. You see what's happening? You're methodically collecting value points exactly how the marking scheme dictates. But wait, here is another major mark trap that honestly breaks my heart as an evaluator. Students find A equals 150 and D equals 25. They draw a nice little box around it and move on to the next page. Do not stop there. Read the final sentence of the question again. It usually asks something like, find his everyday's earning. The examiner specifically reserves the final full 1 mark for explicitly writing out the final sequence. You must write out 150, 175, 200, 225, 250, 275. If you don't write that list, you lose 25% of the total marks for that question, even if your algebra was absolutely flawless. So, before you walk into that exam hall, I want you to mentally engrave this checklist into your brain. Number 1, double-check your signs, especially the sign of D during simultaneous equation subtraction. Number 2, always write the base formula first to claim that guaranteed half mark. Number 3, include proper brackets in your SN sum formulas to avoid silly calculation errors. And number 4, explicitly write out the final sequence if the word problem requests it. Listen, as a veteran evaluator, I want to award you every single point possible, but I can only give you marks for what is actually written on the paper, matching the exact blueprint we discussed today. The math is in your head, for sure, but the strategy must be on the page. So the choice is yours. Are you going to leave those easy half marks on the table, or will you play the game by the rules, write down the exact formulas, and claim the value points that rightfully belong to you? Get in there and crush that exam.